Good afternoon, everyone. I hope you have enjoyed the lunch very much, as I did. Yeah. So welcome to this corrosion fatigue session 2. My name is Jianying He. I'm professor in nanomechanics from Norwegian University of Science and Technology, and I'm honored to be chair of this session. We initially planned to have 3 presentations, but now it turns out we will only have 1 presentation given by Aidin Barabi from Polytech Montreal. So now you probably have plenty of time to discuss your work and to have a good discussion here. Yeah, yes, please. Sure.
So good afternoon, everyone. I'm Aidin Barabi, and I'm going to present part of my PhD project, which is entitled Corrosion Fatigue Crack Growth, Corrosion Fatigue Crack Tip pH Estimation of 13 chromium 4 nickel Martensitic stainless steel. So my project was in collaboration with our industrial partner, Hydro-Quebec. They are producing the main electricity producer in Quebec province. So they produce around 95% of electricity in Quebec province. And in this industry, one of the critical components that they are dealing with is a Francis turbine, which is this picture, and the size of it, if I want to just give an idea for you, it's beyond the size of this room, this component. So this component is made out of low carbon martensitic stainless steel that has a good combination of corrosion and corrosion resistance and mechanical properties. However, during the service condition, it's exposed to cyclic loading and aqueous environment. So basically, the stainless steel that has a protective passive film, during the cyclic loading, the passive film will be broken down and the bare material will be in contact with the water. So basically, we have the corrosion fatigue that is an issue in such components. So here we want to understand what is the impact of environment on the corrosion fatigue crack growth. Would it accelerate or decelerate the fatigue crack growth rate? So we defined 2 questions to answer: how to estimate the crack tip electrochemical parameters, and what is the impact of these parameters on the fatigue crack growth behavior. So if I want to just have a brief literature review on the crack tip electrochemistry, what is going on locally at the tip of the crack, I would say when the crack is formed and is propagating at the tip of the crack, the bare material is in contact with the environment, and we have the anodic half-cell reaction that is taking place, which meaning that we have the release of iron and chromium ions into the solution. And at the same time, we have a counterbalancing half-cell reaction that is happening, which is cathodic half-cell reaction, which at root of the crack is hydrogen reduction reaction, which is called also water reduction, because at the root of the crack, there is no oxygen and the oxygen is consumed pretty much rapid. So the water reduction is the half-cell reaction that is carrying on the oxidation process. So when this happens, this reaction takes place, there is the possibility of the absorption of hydrogen to the walls of the crack and diffusion inside the crack, going towards the plastic zone behind the crack and causing the hydrogen embrittlement. So basically, hydrogen embrittlement is one of the most important damage mechanisms in corrosion fatigue. Apart from this half-cell reaction, there is also another half-cell reaction that is taking place, which is oxygen reduction reaction, because and this reaction is happening outside the crack mouth. So it's at the exterior part of the crack, which we have a lot of oxygen, and it can carry on this half-cell reaction there. So as I said, like at the root of the crack, basically we don't have any oxygen and it's all consumed. So because of this oxygen consumption, the potential would drop at the root of the crack, and in the interior of the crack and exterior of the crack, the potential is different, as it has been reported in the literature that internally the potential has been measured, and at the external of the crack also measured and plotted here. And you can see that we have a potential drop inside the crack comparing to the exterior part of the crack. The other parameter that is dropping its value when it enters inside a crack is the pH. So at the root of the crack, the pH is so low, it's going towards more acidic pH. So it's because the metallic ions are released and we have the formation of chlorides at the root of the crack, which are more of chromium chloride or iron chloride. So these are acidifying the root of the crack and causing the pH drop locally there. And the main elements in the alloys, especially in the stainless steel, is the chromium content that is acidifying. And it has been reported in the literature, as we increase the chromium content in the alloy, the pH drop is increasing, and is the most dramatic one is 1.8 that has been dropped. So based on this, we can see that locally in a tiny crack, we normally have different electrochemical parameters comparing to the bulk solution. And in the literature, they have proposed to, for example, drilling a hole and inserting a microelectrode behind the crack, or inserting it inside the crack, which either of these cases is not good for the crack because it's modifying the crack propagation path and the crack propagation rate. So it's better to avoid that and trying to find an alternative to measuring the crack electrochemical parameters at the root of the crack, and trying to understand what are the environmental damage, whether it is hydrogen embrittlement or anodic dissolution that is playing role. So the objective that we have defined in this presentation is to estimating the concentration of hydrogen at the crack tip. So for doing that and reaching the objective, we have defined several milestones. So we'll start from propagating a crack in the air and water, and then we continue to analyze the corrosion products on the fracture surface, and using the thermodynamic calculation and plotting the Pube diagram, and using these tools, we are able to estimate the pH at the root of the crack thermodynamically, and then we are able to, with the pH, we are able to estimate the concentration of hydrogen. So I carry on to the methodology, and in the methodology, we have first of all designed a corrosion fatigue setup that you can see in the picture, and then we followed the ASTM E647 standard to do the crack propagation. And we have measured in terms of electrochemical parameters, we have measured only open circuit potential with the reference electrode that is placed here in the setup. And then in terms of the mechanical parameters, the delta K was kept constant at the value of 15, and load ratio was kept constant at 0.1. And the reason for that is to make the plastic zone ahead of the crack to be constant, so that we have one single parameter, that is frequency that is changing, and the environment that we are conducting the test in the air and water. Then once the sample was done, we broke it in half and we analyzed the corrosion products using XPS analysis. And then we tried to plot the Pube diagram using thermodynamic calculations by using fact state software. And then we started to do our estimations on the hydrogen concentration. So here we have measured all the fatigue crack growth rates in the air and water. As you can see on the main axis, we have the fatigue crack growth rate as a function of loading frequency. And on the secondary axis is the open circuit potential that we have measured. And what you can observe in this graph is, as we are decreasing the loading frequency, the fatigue crack growth rate in the water, which is the black line, is increasing. And at 0.1 Hertz, we have the significant increment of the fatigue crack growth rate comparing to the results in the air. So then we have observed the open circuit potential, and we have seen that the potential at 0.1 Hertz, which we have the most accelerated corrosion fatigue rate, was more noble. The open circuit potential was going towards more noble potentials. And it is in agreement with the observation on the fracture surface that we have detected only 4% corrosion products on the surface, meaning that anodic dissolution was not playing a role. So we were asking ourselves, what is the reason that we have higher corrosion fatigue crack growth rate at 0.1 Hertz? So we brought up this hypothesis that it could be the hydrogen embrittlement, and that's why we are going after measurement of the hydrogen and estimation of the hydrogen at the crack tip. So we followed our strategy that we defined before, and we analyzed the corrosion products at 10 Hertz and 0.1 Hertz using XPS analysis. And what we have measured, what we have detected on the surface is that we had a chromium oxide, which is the passive layer, and the iron oxides that formed on the fracture surface, and a corundum called FeCr2O4 on the fracture surface on both of the loading frequencies for sure. But the difference was the amount of it. So FeCr2O4 and iron oxide was less observed on the fracture surface, but the chromium oxide, which is a passive film, was more observable at 0.1 hertz, but at 10 hertz, it was more of the corundum and iron oxide. So we have plotted the Pourbaix diagram, and we have with Faxate software, and based on the measurement of the bulk solution for the pH and potential, you can see that this is the red dot, which is showing the properties, electrochemical parameters that we have measured in the bulk solution, that based on the thermodynamic predictions, we should have iron oxide, that corundum of FeCr2O4 and NiO Fe2O3. However, our measurements with XPS shows that we have a pH drop towards this region, that we have iron oxides and FeCr2O4. So this shows that we have a pH drop, but we don't know 100% it's in what range. So we wanted to make it as precise as possible. So we have run the fatigue crack growth test in the deaerated solution as well, and we have measured the open circuit potential, because we said that the oxygen at the root of the crack is not existing. So we've removed the oxygen from the entire solution, and we have measured the open circuit potential during the propagation of the crack. So what we have measured is the potential drop from 0.75 to minus 0.09 volts. And with that, we were able to narrow down our range and estimating the pH of 4.4 to 4.6 approximately. So having this pH, we were able to estimate the concentration of the hydrogen in the electrolyte that we had. And with that, we have solved the second fixed law equation to plot the profile of the hydrogen inside the material from the crack tip towards inside the material. So what you're observing here is that the hydrogen concentration is decreasing as we are going further away from the crack tip. And the hydrogen concentration seems to be more in the 0.1 applied loading frequency of 0.1 hertz comparing to the other loading frequencies. So we have also calculated the accumulated hydrogen at the tip of the crack at each loading frequency. And what we have observed is that we have higher hydrogen that is accumulated at 0.1 hertz comparing to the other loading frequencies. And it was higher than the hydrogen in the bulk material that is inherently exists in the material. So this is because of the fact that at 0.1 hertz, the crack growth speed is slower in terms of dA over dt, not dA over dN. So there is enough time for the hydrogen to diffuse inside the material and goes towards the plastic zone and cause the hydrogen embrittlement. So basically, these estimations is confirming our hypothesis that hydrogen embrittlement is the active environmental damage mechanism in our material at this applied loading frequency. To wrap up, I would say corrosion fatigue crack growth rate in the water at applied loading frequency of 0.1 hertz is higher than the fatigue crack growth rate in the air. And the corrosion product analysis shows that we have oxides and the FeCr2O4 corundum on the fractured surface. And using these oxides and the Pourbaix diagram, we were able to estimate the pH. And using this pH, we were able to estimate the hydrogen concentration at the root of the crack. So with these findings, we were able to tell that hydrogen embrittlement is the damage mechanism at 0.1 hertz. So in terms of the significance of the work, I would say because we were working with the Hydro-Quebec on the hydraulic turbines. So the service condition of the hydraulic turbine consists of two separate load frequencies. The first one is low frequency condition, and the second one is the high loading frequencies. So in terms of the low loading frequencies, we have analyzed that hydrogen embrittlement is the main damage mechanism that is accelerating the fatigue crack growth rate. However, in the high applied loading frequency, it's more of anodic dissolution that is an active mechanism, and it's not accelerating the fatigue crack growth rate for some certain reasons that are out of the scope of this presentation. So our suggestion to our industrial partner is to use the corrosion fatigue crack growth rate at low applied loading frequencies for the estimation of service life and damage tolerance approach models that they have. So for the future works, I'm suggesting to developing a methodology to measuring hydrogen at the crack tip, because before they've used APT to measure hydrogen in the bulk material, but they haven't used it to measure the hydrogen concentration at the root of the crack in the plastic zone. And then I'm suggesting to measure the electrochemical parameters locally at the root of the crack, because before it has been just measured in the crevice-like cracks or pits, and it was not the actual crack. So that's the other suggestion. And the last suggestion is investigating the actual fatigue resistance of the notch sample, because before it has been conducted on the smooth sample, not the notch sample. So it's my last suggestion that I have to the community. So these are the references I've used so far, and thanks for your attention.